So we are going to today start with the notion of band-limited signals. Now the notion of band-limited signals is much more general than just one-dimensional or even continuous time. But to start with, we will talk about the case of one-dimensional continuous time band-limited signals. We will then, after we cover this, we will move on to multiple dimensional signals like images and so forth, and even the notion of discrete time band-limited signals. Okay. So right now we are going to work with continuous one-dimensional. So there is a mathematical definition. Since we are starting with the notion of we have a mathematical signal model, there is a mathematical definition of what do we mean by band-limited signals. And then there is a physical interpretation of that. We'll start off with the mathematical definition, which is given in terms of the Fourier transform, the continuous time Fourier transform. So just to remind you, we have that every finite energy signal x of t has a continuous time Fourier transform. And we'll stick with your book's notation, which is that your x of capital X, j capital omega, that is the notation for the continuous time Fourier transform of a signal. X of t is given by integration from minus infinity to infinity, x of t e to the minus j capital omega t dt. Now this exists, and by exists I mean that x of j omega absolute value is less than infinity for all capital omega in minus infinity to infinity. So this is what I am going to mean here by exist. This transform exists as long as your signal is finite energy. Now, what does finite energy mean? The classical definition is you take the integration of the absolute value square of the signal. Okay? If you do that from minus infinity to infinity, and you have dt, if this is less than infinity, then this means that x of t is finite energy. Okay. Now it is important to keep in mind this absolute value because x of t can take complex values. Okay. So if you just say x of t squared, that wouldn't make sense for complex value signals. Okay. Now, in terms of notation, I'm going to use the same notation, so you should be familiar with this. Signals which satisfy this finite energy signal, it's actually a special class which is called L2R if they are real valued. I'm right now going to stick with real valued. And that class is defined as all functions such that the function energy is finite. And I won't go into the technical details, but this L2R is essentially, if you care to find out about it, it's a Hilbert space, and you can define notions of norms and inner products on this space. But right now we'll forego that discussion. I just want to, just as a shorthand for finite energy, I'm going to use L2R. Okay. Now omega here is Some of you might have seen it differently. Omega here is the radians per second frequency. Some of you might have seen it in hertz. Well, that has a little bit, there is just a scalar factor, 2 pi difference. Now, if the signal is finite energy, then you have a Fourier transform, which is defined by this expression. And what we say is, we write that x of t has a Fourier transform pair. This is the notation I'm going to use, x of j omega. And from the Fourier transform, you can recover the signal itself. So you have the inverse Fourier transform expression, which is that x of t equals 1 over 2 pi minus infinity to infinity x of j omega e to the j omega t d omega. Okay. Now, for people, and I realize that some of you might have seen it in hertz rather than in radians per second. I'm just going to express that, but since our text deals with radians per second, we are going to stick with radians per second. The relationship is only a factor of 2 pi. So if you want to write Fourier transform in hertz, that is given by x of t. You have a relationship. Fourier transform will write x of jf. This is in hertz, and the expression, the formula for x of jf, of course, is the same, except that instead of capital omega, you use 2 pi f. So you get minus infinity to infinity x of t e to the minus j 2 pi f df. And likewise, your x of t now is exactly the same as the radians per second inverse transform, with the only difference being that you don't have the factor of 1 over 2 pi. And that you can find out why that is the case by simply doing a change of variables. So in that case, what you get is minus infinity to infinity x of jf e to the j 2 pi f. This should be dt, and this is df. Okay, so in that case, the frequency is stated in terms of hertz. If you have seen that, since our book uses radians per second, I'm going to stick with radians per second. But hopefully that won't create a confusion for any one of you. Oh, you mean here there should be a t, right? Yeah. Thank you. Yes. Okay, so this is just the definition. I wanted to remind you of the Fourier transform, continuous time Fourier transform. Again, I presume all of you have seen that multiple times. So the definition of band-limited signals is what we are after. Our mathematical model here is that we are going to focus on signals that are band-limited, and the mathematical definition of that is I am going to use the notation BL omega n L2R. I hope everyone understands that this means a real line, this R that I'm drawing. So the definition of band-limited signals is all finite energy signals such that their Fourier transform is identically 0 for all omega greater than or equal to omega n, absolute value. Okay, this is the definition of a band-limited signal, a signal which is band-limited to omega n radians per second. This is just the plain mathematical definition. All finite energy signals. Why finite energy? Because if we don't have finite energy, then we cannot define the Fourier transform. So all finite energy signals, then their Fourier transform is defined, and if their transform is 0 outside a certain range, outside an interval minus omega into omega n, then they are band limited signals. That's the mathematical model that we are going to begin with. Now, if you think about examples of this, you can draw plenty examples. We'll time and again stick with the same classical figure. So the example of this is if this is the Fourier transform of your signal, then this is a band limited signal because the Fourier transform becomes 0 after omega n. Okay. Now, if on the other hand we have a Fourier transform like this, this is not a band limited signal. If our omega n is here, so the upper one belongs to the band limited signal, and the lower one does not belong to the class of band limited signals. This is just the plain mathematical definition. We are well within our right to define anything that we like, and we can say we want to state a sampling theorem for this. The question is, what does the mathematical model of band limited signals mean? And that relates to the interpretation of the Fourier transform. Now, finite energy signals, as we will go along and see, they can actually, you already have seen transforms like Laplace transform and Fourier transform, I'm sure, in your undergraduate studies. But finite energy signals can have many other types of transforms, and not every transform may have a very neat physical interpretation. While you can try to understand what does that transform mean, it may not have a very neat physical interpretation. The reason we really find a ubiquitous use of Fourier transform in the real world is because the Fourier transform has a real world interpretation in terms of frequencies. Okay? So what if we try to understand, if we try to look at the formula of Fourier transform and look at it again, remember that we say x of t is equal to 1 over 2 pi minus infinity to infinity x of j omega e to the j omega t d omega. And if you try to interpret it, what is this saying? What is e to the j omega t? It's just a complex exponential. It's a sinusoid, right? It's a complex sinusoid. So this is a frequency, this is a sinusoid, complex exponential, or I'll just abuse the notation and say sinusoid of frequency omega radians per second. Okay. And this is a number associated with that frequency. This is just a scalar, and we can think of it as amplitude and phase of that frequency. So if you look at it from that perspective, what Fourier transform is telling you is, now this integration, of course, is just an infinite summation taken to the limit. Think of the Riemannian integration is just an infinite amount of summation taken to the limit. So what this formula is telling you is, your finite energy signal is made up of an infinite number of sinusoids, and the amplitude of each sinusoid is given by your Fourier transform at that location. Okay? So you have, but the reason Fourier transform has a physical interpretation is it is at some level telling you what kind of frequencies exist in your signal, and in our real world we have a good sense of what does frequency mean. What is the meaning of frequency in a very crude sense? The rate at which your signal wiggles or it oscillates, that's the notion of frequency. So frequency has a physical meaning to us, and Fourier transform essentially is saying your signal can be thought of as made up of an infinite number of frequencies, and the Fourier transform tells us which frequency has how much amplitude associated with it. So if a frequency has too much xj omega is very large for some omega, that means we have more of that frequency present in the signal. Okay? So the notion of band-limited signals essentially means then that your signal has no frequency after omega n radians per second, or omega n over 2 pi hertz. So if a signal is band-limited, it means the signal does not have very high frequencies. Right? If omega n, let's say, is 2 pi times a megahertz, then your signal has no frequency bigger than 1 megahertz. So the physical interpretation of the mathematical model, the meaning of the mathematical model of band-limited signals is that a band-limited signal contains no frequency above omega n radians per second, or omega n over 2 pi hertz. Now, why we are dealing with then this mathematical model, or why do we believe that we should be able to sample a band-limited signal? Because what we are saying is that our signal doesn't have too high frequencies, so it cannot wiggle too fast or oscillate too fast. And if it cannot oscillate too fast, then the hope is that we can take some measurements of our signal and still be able to represent it, recover it, or know everything that there is to know about it. Just like the case of the constant signal we saw earlier, where just one sample is enough to describe all the information. A band-limited signal can be described by a few samples taken at the right locations. Okay? So that's the hope. And just to give you a sense, in case you have forgotten, example of, for example, delta t. Everyone hopefully knows this direct delta thing, delta t. Right? It's the fastest, it's the signal that can change at the fastest rate. It's supposed to, it's zero everywhere, and all of a sudden it shoots so high that the total integration becomes 1. So nothing can change faster than impulse. Now, does anyone remember the Fourier transform of the direct delta? It's 1 for all capital omega. What does that mean? That means that since your signal has wiggled so fast, it has all frequencies present in it. All the frequencies are present at the same rate 1. Now, what's the other extreme? We saw that already. The other extreme is a signal which is 1 for all t. What is that signal? It's a constant signal. And a constant signal, anyone remember the Fourier transform of the constant signal? It's 2 pi delta of omega. which means that the Fourier transform is 0 for all frequencies other than omega equals 0, which is what makes logical sense. This signal does not change at all. It doesn't wiggle at all. It has no oscillation whatsoever. And if it has no oscillation, then it means it contains essentially no frequencies except 0. And that's why the Fourier transform is just non-zero at 0, omega equal to 0. So hopefully that will give you a sense of what is the physical meaning of Fourier transform and why we are interested in band-limited signals, because a signal being band-limited tells us it cannot wiggle forever, wiggle too fast. It has to oscillate at some manageable rate. And that's why we want to study band-limited signals. If you tell me how to sample, for example, a direct delta, the only way is you really have to know where the direct delta exists, because it wiggles so fast, you sample it anywhere else and you're going to miss the information. So we have to work with band-limited signal. So just like the case of constant signals, we should be asking the same question. Okay, it's a good signal model. Why does this signal model matter in the world of engineering? And the answer is that in many contexts, we can model what we are doing, our engineering systems, as dealing with band-limited signals, or at least dealing with approximately band-limited signals. So two classical examples of band-limited signals are number one is voice recording or even music. Now, human ear cannot detect most, or at least most humans, or I would say a majority of humans, cannot detect frequencies. Our ears can't detect them above 20 kilohertz. So even there is some noise or some sound above 20 kilohertz, we are not going to hear it anyways. So if we are recording something for human consumption, then we may as well treat the signal that our human ears are hearing as band limited to 20 kilohertz. Okay? So can be considered band limited to belonging to 2 pi times 20 kilohertz. The other engineering example is, for example, a category 5 copper wire. So it's just a term that is used for the copper wire, Cat 5 copper wire. Now this copper wire, if you transmit a signal through this copper wire, it has very strong attenuation above 100 megahertz. So this category 5 copper wire essentially can only carry frequencies of 100 megahertz. If you are transmitting anything on that copper wire, then it doesn't make sense to treat it anything other than 100 megahertz, a signal which is band limited to 100 megahertz. Okay. And there are, of course, numerous examples. In real world, you are not going to find perfectly band-limited signals. There are always approximations involved. And one of the classical examples that is given, of course, is due to the duality. I hope you remember from your undergraduate Fourier transform that a signal, if it becomes 0 in time, then it has to be infinite in frequency. And a signal, if it is it becomes zero in frequency and stays zero, then it has to be infinite in time. Infinite, not value, but it must take non-zero values for infinite time duration. So any band-limited signal has to exist from minus infinity to infinity. Now, no matter which application we are dealing with, we are not going to ever look at it from minus infinity to infinity. So band-limited signals, in reality, there is no such thing as a band-limited signal that we observe, but they are good approximations. And because of the physical reality, we deal with band-limited signals pretty frequently in all kinds of devices. Okay? So that is the reason we are interested in band-limited signals. And the question that we want to address is, once we have defined the class of band-limited signals, we want to figure out sampling theory for band-limited signals. So the first thing, once we have nailed down the mathematical model, which is the band-limited signals, we have to specify what kind of sampling strategies we are going to use. To begin with, we are going to assume a very particular kind of sampling strategy, which is called, so our sampling strategy is going to be uniform and pointwise sampling. Why uniform and pointwise? Because in terms of hardware, that is one of the easiest ways to do sampling, although that is not the only way to do sampling. There exists beautiful theory for non-uniform sampling, for example. Okay. We may or may not get a chance to go to that topic. But right now, we are going to not only fix our mathematical model, but also fix our sampling strategy. And what the uniform pointwise sampling means is that a signal comes in and you take samples of that signal every t seconds to get x and a discrete sequence given by x and t for n equals 0, plus minus 1, plus minus 2, and so forth. Okay. So why uniform? Because we are taking samples every t seconds. Why pointwise? Because every t seconds we just measure what the signal is at that point. Okay. And another figure that you will see in your text is that you have x of t, and you have a block which is called continuous to discrete, and you have capital T, and at the end you get xn. Now this T is termed sampling time. Associated with this sampling time is something called sampling frequency, which is given by 2 pi over t. This is in radians per second. If you want it in hertz, then that is simply given by 1 over t. So that is sampling frequency in hertz. And pictorially, what you have is that you have a signal, let's say this is your signal x of t, and what you do is at every t seconds, you close a switch, and that switch figures out what is the value of the signal at that point. So let's say this is t equal to 0. This is t equal to capital T. This is t equal to 2t. T equal to minus t. And the value that you get at t equal to 0, we'll call that x0. The value you get at t equal to capital T, that's x1. And the value at minus t is x minus 1, and so forth. Okay. Now, if we have specified the mathematical model and we have specified the sampling strategy, then the next question we want to address is how many samples are necessary and sufficient to take this sequence and get back x of t. Now, the question of samples in this problem, if you look at the picture closely, right, the only variable that is left once we have specified that it's uniform and pointwise sampling, what is the only variable that is left for us to tweak? It's the sampling time capital T, or the sampling frequency, either way. So what we have to answer is, since the only variable in our hands is omega s, I'm going to now move to sampling frequency omega s. The only variable in our hands is omega s. So the question we need to address is, how should omega s be picked such that we can ensure xn helps us get back to x of t. And that's what we are going to show. What should omega s be? And that will lead us to the classical Shannon-Nyquist sampling theorem. Okay. In reality, this sampling theorem should be attributable to 4 people. It's Shannon-Nyquist, there was another guy, Whittaker, and another guy, Kotelnikov. So to answer this question, we really have to put this into a mathematical framework that we can use to say, we are going from xt to xn, what is going on in between, and how do we make sure that we don't lose any information when we go from xt to xn. Now for that, we are going to rely upon, first of all, some properties of the Fourier transform, and I want to remind you of those properties in case you have forgotten. We are not going to cover those here, though. So some properties of Dirac delta and continuous time Fourier transform, which we will need for our analysis. Okay. The first property is that of the sifting property. It's not shifting, it's sifting property, which is that if you multiply a function f of x, I'm now using just the general term f of x, with the Dirac delta of x minus x naught, then the output is simply the function value at x naught times the Dirac delta. Okay. We multiply a signal with the impulse, and you get back the impulse with its area scaled by the function value at that point. The second property we are going to need is the multiplication in time and convolution in frequency property. So if you have two signals, x1 of t and x2 of t, and you take their Fourier transform, then their Fourier transform, at least in radians per second way, that is given by multiplication in time is always given by, in terms of Fourier transform, convolution in the Fourier domain. So it's 1 over 2 pi x1 j omega convolved with x2 of j omega. Again, 1 over 2 pi factor here is because we are dealing with the radians per second notation. Okay. The third property is that if you convolve a function with an impulse that is shifted to x0, then what happens to the function? If you convolve a function with a shifted impulse, with a shifted Dirac delta, then the only thing that does is it shifts your function to the location of the Dirac delta. Okay? And this is very easy to prove if you use the shifting property. You can go home and try it out. Now the fourth property that we need, which I have given you as a problem, practice problem set, which hopefully you can prove, is that if you have an impulse train or a Dirac train, so an impulse train S of t equals summation n equals minus infinity to infinity delta of t minus nt. Okay. What is this? Simply a collection of impulses separated by t. Right? The Fourier transform of this impulse train is S of j omega is another impulse train. Okay? So the Fourier transform of an impulse train is an impulse train which is scaled by 2 pi over t, and its separation is given by the sampling frequency 2 pi over t times k. Okay? So if you look at, if this is your S of t, then what you get back is another impulse train. The Fourier transform is still an impulse train. The only thing that happens is that the height of this impulse train becomes, or the areas of the impulses become 2 pi over t. And they are located at omega s equal to 2 pi over t, 2 omega s, and so forth. Okay? So these are the four properties that we are going to use to help us figure out what should be the sampling rate or the sampling frequency we should use to make sure we can recover band-limited signals from their samples. So using these these four properties, the shifting property, the multiplication in time equals convolution in frequency property, convolution with a direct delta gives us shifting of the function, and finally the Fourier transform of the impulse train. We are ready to figure out what happens when we take samples of a band-limited signal. So mathematically, we are now going to characterize our sampling operation. What we originally said was that xn is given by xnt, and in terms of architecture, we said we can build it like this, a switch which closes every t seconds, and at the output we get xn. Now to help us analyze, we are going to convert this architecture into a little bit of a different shape, which will have more components, but the end-to-end function remains the same. So let's look at that. We can get xn in two fashions. We get our xt and we multiply that with an impulse train s of t. Okay. The impulse train being what I just showed you earlier, which is there is an impulse every t seconds. And then once I multiply it with the impulse train, I then convert from impulse train to sequences, and I get xn. And I express this whole thing as the mathematical abstraction of this switch. So there is a factor of t going in here. Why we are going to replace this hardware or this schematic with this elaborate setup is because it helps us do the analysis. So let's see what is happening. What we are saying is that we have a function. Let's say this is our function. Okay, this is our xt, and we can multiply that with an impulse train which has period capital T. So we have an impulse train where the area of the impulses is 1, minus 2t, minus t, t, 2t. Now by the shifting property, if we multiply this function with this impulse train, what's going to happen? We are going to be left with only impulses with an impulse train, but the impulse train will, the areas of those impulses will be simply scaled by the function values at that time. So what we end up with when we do the multiplication, if this is my impulse train, I get something which I'm going to call xs of t. That will be simply another impulse train, but this will be, the area of this will be equal to x of 0. The area of the next impulse will be equal to x of capital T. The area of next one will be equal to x of 2t. Similarly here, I will have x of minus t. Okay. And this is 0, t, 2t, minus t, and so forth. So when I multiply my function with my signal with an impulse train, I get back another impulse train with the only thing happening is that my amplitude gets scaled. My area of the impulses gets scaled. Now, the next operation, if you go back, we have this operation of convert from impulse train to sequence. Well, if you look at this, your x0, you can simply now read the areas of these impulses and put that into your sequence. Okay, so this you can put that in x of 0, your sequence, this in x of 1, this is equal to x of 2, this is equal to x of -1, and so forth. Okay, so at the end of the end-to-end relation doesn't change. We start with the signal and we get its samples every t seconds, but doing this mathematical formulation helps us do the analysis a little better. So what is happening is, in our now new mathematical framework, we are starting with x of t. We are then going to xs of t, which is equal to x of t times s of t, the impulse train. And then we are going to x of n. To figure out whether we can recover xt, we need to make sure that we can now go back to this. There's a question mark. And from here, can we go back to this? There's a question mark. If you actually focus at this part, going back and forth between the impulse train and xn is very simple. If you are given the impulse train, you simply read the values and you put them in the sequence. If someone has given you the sequence, you just create an impulse train with the area being equal to the value of the sequence. So this question mark that we have here is actually very easy to deal with. We know that the mapping, if you want to use mathematical terminology, the mapping between xs and xn, it's invertible. You can go from xs to xn and xn to xs. That is not a challenge. The challenge is, when can you go from this xs t back to x of t? So rather than now focusing on when can we go from xn to x of t, the only question we need to ask ourselves is, when can we go from xs t to x of t? So what we are now going to do is try to figure out when going from when we can go from xs t to xt back and forth without ever losing any information. So for that, rather than looking at the time domain signal, what we are going to do is we are going to look at the frequency domain. We are going to look at the Fourier transform of xst. Because since Fourier transform, it's equivalent whether we talk about the signal or its Fourier transform. If we can say that from the Fourier transform of xs, we can go back to the Fourier transform of my original signal, it's equivalent to saying I can go from xst to xt. So what we will do is look at Fourier transform of xs of t, which I'm going to write xs j omega. So let's do that. Fourier xs j omega is simply Fourier transform of s of t times x of t. Now we just did a property of the Fourier transform that if you are interested in computing the Fourier transform of signals which are multiplying, what happens? You get convolution of their Fourier transform. So we get Fourier transform of x of t convolved with Fourier transform of s of t. Okay, by definition, I am writing this thing as x of j omega. Okay. Now, what is the Fourier transform of the impulse train? We computed it again previously. The Fourier transform of an impulse train is another impulse train. So we have 2 pi over t, k equals minus infinity to infinity, delta of omega minus k omega s. Okay, where this omega s is 2 pi over t. Okay, now hopefully you guys remember that convolution is a linear operation. So I can take this thing inside the summation and compute convolution of this thing with each individual impulse. So what I get is 1 over t, because this 2 pi and this 2 pi cancels, summation k is minus infinity to infinity, x of j omega convolved with delta of omega minus k omega s. We have used all the all the properties that we discussed earlier except one, which is what happens when you convolve a function with a shifted direct delta, with a shifted impulse. It is going to, this whole thing is going to be just shifted to omega s. So our answer is 1 over t summation k equals minus infinity to infinity x of j omega minus k omega s. So what is happening here is that when we multiply our signal with an impulse train and we look at the Fourier transform of that signal, the multiplied signal, what we are getting is we have this summation means we have multiple copies of the original signal's Fourier transform shifted at k omega s, shifted at different multiples of sampling frequencies, and each copy is scaled by 1 over t. So if we want to ask the question, when can we go from xst to x of t, essentially asking when is the mapping between xt and xst is invertible, that is equivalent to asking when can we go from the Fourier transform of xst, which is xs j omega, to x of j omega. Xs j omega contains multiple copies of x of j omega, but we have to make sure that these copies don't get corrupted. So the question is, when does that happen? For that, you can, of course, look at it mathematically too. You can stare at this expression and see when does x of j omega doesn't go bad, but we'll try to look at it pictorially to help us understand it a little better. So assume that this is your function x of j omega, okay, And we are going to assume that it is band limited, because that's our mathematical model. When we multiply it with the impulse train, so when we do x of t, s of t, we get xs of j omega, which is, so let's call the height of this thing a. So we get this Fourier transform xs j omega, which has multiple copies, as you can see here. So the first copy is centered at 0. Okay. This is, and the height of this is a over t. There is a scaling of 1 over t. And this endpoint is minus omega n and omega n. Now we have an additional copy at omega s. So we have a copy at omega s. Okay. The height of that copy is still a over t. Okay. And we have an additional, actually let me do this. And we have an additional copy at minus omega s. The height is still a over t. And this, of course, continues, because we have an infinite copy. But it is okay to look at the middle 3 copies, because whatever is happening there is just happening everywhere else. It's a periodic repetition. Okay, so we are looking for xj of omega in xs j omega. Let's look at the endpoints of this. We know the endpoint here is this, and the endpoint here is omega n. Let's look at the endpoint of this copy. What is the endpoint of this copy? That is omega s minus omega n. And what is the endpoint of this copy? Minus omega s plus omega n. So what I have drawn is true only if this thing is what? If this thing is bigger than or equal to omega n. Otherwise, the diagram I have created here is wrong, because then this endpoint is smaller than omega n. It will be here. Okay? So there are 2 cases to consider. One case is exactly what I have drawn. That case says that if omega s minus omega n, and you can use this version too, it will give you the same answer, is greater than or equal to omega n, which means if and only if omega s is greater than or equal to 2 omega n, if that happens, then you actually can see that x of j omega exists in xs j omega. It is there in an uncorrupted fashion in its real form. How we recover that is a different thing, but mathematically it is there. You can look at it in this picture, and you should be able to recover that xj of omega. Okay? The other case, of course, is that this is not true. What if actually omega s is less than 2 omega n? Then we have an overlap of different copies. So let's take a look at what will this above picture look like in that case. We'll again have minus omega n a over t. But in that case, this copy will come here, and in here is a point you can verify that they intersect, at least in this case, at omega s over 2. Okay, this point is omega s, and similarly you have an overlap here at minus omega s. This overlap will happen at minus omega s over 2. And when you add them up, what you get is that up to this point, the addition of this will look like this. So effectively, what you get is a figure like this, where these endpoints are omega s by 2, omega s by 2. Okay. And now if you ask yourself, can I see xj of omega in this picture, or can I, or is the map between x and x of s is invertible? The answer is no, because clearly we know that this, the xj of omega that we started with, this one, this thing gives us this map. But another map that will give us another function or another signal which will give us the same map will be, which was band limit, which had a frequency of minus omega s by 2 and omega s by 2 and minus omega s by 2 and a. So another x prime j omega, if we multiply that with the impulse train, it will also give us the same thing. So if someone shows you this picture, you can't really tell whether my signal was x of j omega or x prime of j omega. Okay. So it's clear that if you have omega s is less than 2 omega n, you don't have an invertible map. You cannot go back from xs to t to x of t. Okay. So what we have so far shown is a necessary condition. Okay. Why necessary? Because I haven't really told you how to recover in the previous case the original signal. We have seen, at least in this case, we don't have an invertible map. There are two signals that map to the same xs j omega. Hopefully you guys remember from your basic undergraduate mathematics that for a map, for a function to be invertible, right, it has to be it has to be a bijection, and so two things cannot point to the same thing. So we have here we have a necessary condition, at least, is that omega s has to be greater than or equal to 2 omega n, because we have seen if that is not the case, because otherwise going from xs j omega to x of j omega is impossible. Okay. Because the map is clearly not invertible. And these are just two signals. I can come up with many signals which will give me the same map. Now let's figure out, is this also a sufficient condition? Sufficient condition means that if this condition is satisfied, then I must have a way of recovering xj of omega from xs j omega. So is this a sufficient condition? To answer that, we just look at the case first pictorially and then we'll do the mathematical analysis. We have shown that if your condition is satisfied, omega is greater than or 2 equal to 2 omega n, then up to minus omega s over 2 and omega s over 2, the same condition will imply that up to omega s over 2 there is no overlap, okay, of the different copies. Now I know that this copy is my x of j omega, although this whole thing is xs of j omega. So what can I do to recover this copy from xs j omega? There's only one way we know how to amplify frequencies and kill frequencies, and that is filtering. We will simply take xs of t and do what? What kind of a filter we will use we'll just use a low pass filter with cutoff frequency minus omega s by 2 and omega s by 2. The only thing is that our low pass filter has to have an amplitude of t, because here the amplitude is a over t. Our original signal had an amplitude of a. So to recover x j omega, we can low pass filter xs j omega, or equivalently we can say xs t, by hr j omega, which is an ideal low pass filter. It has a magnitude of t for all omega less than or equal to omega s over 2 and 0 otherwise. If we do that, then of course we will just have a low pass filter which will be from omega s by 2 to minus omega s by 2. Height will be a over t, and the answer we will get is simply minus omega n to omega n, because omega n is less than omega s over 2 and height a, and this is going to be x j omega. So indeed this shows that the omega s greater than or equal to 2 omega n condition, it's not just necessary, but it's also sufficient to recover a band limited signal from its samples. Just to complete the analysis, we are going to call x r j omega equal to h r j omega times xs j omega and that is simply hr j omega times 1 over t summation k equals minus infinity to infinity x of j omega minus k omega s. Once again, we can just take it inside the summation 1 over t summation k minus infinity to infinity hr j omega will be multiplied by all the copies. But all of these copies other than the one at k equal to 0 are outside the range of this reconstruction filter, so we are only left with one copy, which is 1 over t hr j omega x of j omega, okay, and that is simply equal to x of j omega, because of the fact that hr j omega is a low pass filter between minus omega s by 2 and omega s by 2. Okay. So that's just the proof of the sufficient condition. And this hr j omega, it's called the reconstruction filter, or sometimes, because we are using an ideal low pass filter, it's called ideal reconstruction filter. And that effectively helps us define the state the Shannon-Nyquist sampling theorem. What we have effectively shown is that if you start with the mathematical model of band-limited signals and you do uniform point-wise sampling, then you can take your samples and reconstruct the original signal as long as omega s is greater than or equal to 2 times omega n, the bandwidth of the signal. Okay. So the Shannon-Nyquist sampling theorem is then, using this we can state the Shannon-Nyquist sampling theorem for band-limited signals. The basic assumption of that theorem is that x of t belongs to the class of band-limited signals If that happens, then x of t can be uniquely recovered from its uniform pointwise samples x of n equals to x of nt for n equal to 0, plus minus 1, plus minus 2, so forth, if omega s is greater than or equal to 2 omega, which is 2 omega n, which is of course equivalent to saying that 2 pi over t is greater than or equal to 2 omega n, which is equivalent to saying that omega n is less than or equal to pi by t. Okay. They are all equivalent conditions. Now, in the terminology of sampling theory, this omega n is called the Nyquist frequency, which is simply defined as the highest frequency present in the signal. And 2 omega n is called the Nyquist rate. And the proof of this is effectively by construction, which is we have just done the proof. I'll just repeat the steps. By construction, I mean that you can explicitly state how you will do that. So the proof involves simply 2 steps. Number 1 is once you are given the samples, you simply take those samples and convert it into an impulse train with the areas of the impulses proportional to the samples. So you are given xn, You convert it to an impulse train given by x s of t equals summation n equals minus infinity to infinity x of n delta of t minus nt. And once you have the impulse train, then we just finished doing the final step of the proof, which is you take that signal and you low pass filter x s of t using hr j omega equals to t for omega less than or equal to omega s over 2 and 0 otherwise. Okay. Effectively, you access t is equal to you compute excess t convolution with the filter impulse response hr of t, okay, which is the Fourier transform of your filter, and that is guaranteed to be x of t because of the analysis that we just ended up doing. Okay. So that is pretty much the end of the Shannon-Nyquist sampling theorem. We will just finish it in the next class with a couple of other pieces of information. But the main point is that if you start with the mathematical model of band-limited signals, and if you do uniform point-wise sampling, then you can reconstruct that exactly as long as your sampling frequency is at least twice the maximum frequency in your signal.